Hello, thank you for joining us for this session, Overview of the Lighting System Requirements of the 2019 Oregon Commercial Energy Code. I'm Connie Umfrist, Communications Manager here at New Buildings Institute. Before we begin, I have a couple of housekeeping things to tell you about. First, you are muted and we cannot hear you. This helps keep the background noise down so that everyone can better hear the speakers. I want to direct you to the dashboard that you should be able to see on the right-hand side of your screen. If you are having technical difficulties and cannot see the slides or hear our speakers, you can use the question pane in this dashboard to let us know and we will help you as we go. If we have time, we will take a few questions at the end of the presentation. Please ask questions in this same question pane. If there's not enough time at the end, we will follow up with a personal email. All registrants will receive an email tomorrow with links to this recording and slides for the session. Our speaker today is Sean Denniston, NBI Senior Project Manager. Sean's work at NBI includes analysis and review of data relative to commercial building energy performance and prediction, code and energy program effectiveness, and energy technologies. Sean uses his expertise for code analysis, tool development, and research. He also manages NBI's new construction program, which provides technical resources for new construction projects. Sean, over to you.
Thanks, Connie. So welcome to our third webinar about ASHRAE 90.1 for use in the Oregon Energy Code. For any of you who have joined us for all three webinars, thanks for sticking with us through it all. And I'm sorry that we're going to have to go through the same introductory remarks for any of the new people, but let's start with an introduction to who NBI is. NBI is a nonprofit working to improve the energy efficiency of buildings. We have a couple of areas that we focus in to pursue this end: best practices and new and existing buildings. So this would be guides that we put out into the market, continuous code and policy innovation, and zero energy leadership and market development. Before we begin, we want to thank the Northwest Energy Efficiency Alliance, the Energy Trust of Oregon with ClearResult, for supporting this webinar series for training on the new code. And we want to thank the Pacific Northwest National Lab and the Department of Energy for providing most of the material that went into this training program. I think it's useful to do a little bit of background information on why Oregon is making this change to its energy code. Through both legislation and executive orders, Oregon has some pretty aggressive goals for reducing greenhouse gas emissions and energy consumption in the state of Oregon. And of course, buildings are a big part of that. And so that means trying to bring down the energy and carbon consumption that we see in buildings, and the energy code is one of the prime policy tools to do that. Specifically, some of you may have heard of Executive Order 1720, because it was a pretty big and sweeping statement on what the governor hopes to accomplish in the state of Oregon. And it specifically has direction for the commercial energy code to achieve the levels of efficiency that we see out of national standard codes by October 2022 or even better. And this is part of the reason that Oregon needed to make a shift from its previous code, which was a little bit of a combination of home-brewed requirements developed in Oregon itself and the IECC. The state made the choice to go across to ASHRAE standard 90.1 instead of the code that it had before for a series of reasons, including how the national vetting process and then the many tools that are available for use and the savings analysis that has already been done to streamline the code adoption process in Oregon so that we don't have the same kind of long delays in between energy code updates. And in order to go beyond what the model code's done, Oregon has adopted a zero-ready code. And this is based on the Zero Code produced by Architecture 2030, which is a combination of using ASHRAE standard 90.1 as a basis for performance and then pairing that with on-site and other renewable energy to bring the building performance to zero net energy. Now, the reason that this is a zero ready code and not an actual zero energy code is that unlike the zero code that Architecture 2030 has put together, in Oregon, you won't have to install the renewable energy system. You will only need to calculate the size of renewable energy system that would be required to make your building zero net energy. So performance levels are determined by ASHRAE standard 90.1, and then you do this additional calculation that will let you know how much renewable energy you would have needed to make your building zero net energy. This will be useful for designers who are going through the process to see really what is the gap between their building performance and the amount of renewable energy production that they could conceivably build on site, and begin to adjust their design practices to get closer and closer to zero net energy. Now, to assist in this, Architecture 2030 has actually put out some tools for calculating the size of the renewable energy system that you might need. You can enter in some simple information about your building, like its location, number of stories, how it's used, and then some information about typical renewable energy system that you might install on your building. And with this really pretty simple information using, in most cases for the renewable energy system, you'd be using best practices and what's available on the market. You can calculate the size of the on-site system that you would need to achieve zero energy in your building. It was also recently announced that Oregon has adopted as a statewide alternative method the 2018 edition of the International Energy Conservation Code. So this is to help make this transition into the new codes. It gives greater flexibility. You can still use a code that's based on the I codes, and IECC 2018, while not quite as stringent as ASHRAE 90.1 2016 on average. In some cases, it's actually more stringent. In some cases, it's less. This will provide an option for you to go through for compliance. The structure of 90.1 is, while it's divided into chapters and the numbering is very different than what we've had in Oregon in the past, the order of things and the way things are grouped is still fairly similar. You see that we go through purpose, scope, and definitions in the first 3 chapters. Chapter 4 has administration and enforcement. You might be used to seeing that a little bit earlier. Then we go into building envelope. Then we have a chapter for heating, ventilating, and air conditioning, chapter for service water heating, a dedicated chapter for power. It's short, but it is a standalone chapter for lighting, a chapter for other equipment. And then we have chapter 11, which is using modeled simulation, it's computer modeling for compliance. We have chapter 12, which is the normative references, and then a series of appendices. And you might be very familiar with Appendix A. It's the one that gives you the U factor values for various wall and envelope assemblies so that you can look up your assembly, see what the resulting U factor of that assembly is. It's used, whether or not you're using ASHRAE, a lot of people will use this when they're designing their envelopes. And then Appendix G, which is another modeling methodology that's available within 90.1, a rating model methodology that allows you to see how much you might actually be exceeding the code. The way that 90.1 applies is really how we've seen before. There's not a lot of changes here. It applies to new buildings. It applies to additions pretty much as if they were new buildings, with some exceptions when you're extending systems from the main building into the addition. Alterations, it applies to the scope of the alteration with certain exceptions for certain activities. It applies to new equipment that's going into a building, and then it has criteria for determining compliance with requirements. Unlike the IECC, it does not apply to single-family homes or low-rise multifamily. There is not another section of 90.1 that applies to these types. ASHRAE does have a standard, 90.2, that applies to low-rise residential, including single-family, but that has not been adopted in Oregon at this time. And then 90.1 doesn't apply to buildings that don't use any electricity or fossil fuels. So if you're not importing energy to the site in these forms, then makes sense that you wouldn't apply an energy code to it. There are, as always, certain buildings and elements that may be exempt from the code, either fully or partially. So make sure that you're checking as you are taking on a project, especially if you are less familiar with 90.1. And the caveat of all energy codes is that it's never going to circumvent any safety, health, or environmental requirements that are elsewhere in the code. When you're using 90.1, there are really three compliance paths through it. The prescriptive path, which is the list of requirements, do all these things and you comply. There's the energy cost budget that we mentioned in chapter 11, and then Appendix G. And a thing to point out about Appendix G for anyone who's familiar with ASHRAE is that in the past, Appendix G wasn't technically a code compliance path. A lot of jurisdictions allowed it to be used that way anyway, but the way it was structured, it was really meant to be a rating system. But in 2016, it has been modified so that it is specifically allowed within the standard to be used for code compliance with 90.1. And that's not the only change to Appendix G that we want to make you aware of. We're really talking about power and lighting today, but want to make sure that you understand that Appendix G went through a couple of fairly large changes in 2016. The old kind of equation for rating under Appendix G, the one that you see at the top there, the performance cost index, has been replaced with a new performance cost index methodology where you actually establish a target using a set of variables, including this table here on the right that gets factored into it. And we don't have time to get into how you do Appendix G under 90.1 2016, but we just want to make sure that you're aware that the process is different. So if you want to do modeled compliance using Appendix G, make sure that you take a close look at how things have changed, and there may be some impacts for designs as well. So when we look at the lighting section, in many of the chapters, what we'll have is a prescriptive option, and there is some option for doing trade-offs, and maybe there's a simplified option. It's especially the case in HVAC. But in lighting, we really only have the prescriptive option, and then you can do one of the two modeling approaches. And so that's what we'll cover today in lighting. For power, however, we're really looking, which is where we're going to start, we're looking at all mandatory. So it's really, in some ways, there's not a prescriptive path through because everything is required. And these are things that can't be traded off even if you do modeling. We have 4 basic mandatory requirements here, one for voltage drop, automatic receptacle control, electrical energy monitoring, and low voltage dry type distribution transformer requirements. Want to point out especially automatic receptacle control and electrical energy monitoring. These are 2 requirements that really set 90.1 apart from a lot of other energy codes and from the previous energy code that was in place in Oregon. And so these are something that you'll really need to pay attention to. We're not going to really talk about voltage drop because it really just limits voltage drop to 5%, and it's a pretty simple requirement. And we're going to jump right into automatically controlled receptacles. And what this requirement has is that at least 50% of all of your standard 125 volt, 15 and 20 amp receptacles have to be controlled in specific use type spaces. So private offices, conference rooms, rooms used primarily for printing or copying functions, break rooms, classrooms, and individual workstations. Now, when you look at this, these are really heavily dominated in office space types. And the requirement is that 50% of the receptacles need to be switched, and there's kind of a complex way. There's one way to achieve this that requires more materials, and then there's a simpler way. One way is that you can just use a whole receptacle, the duplex, both plugs in the receptacle, and just put a switched receptacle next to an unswitched receptacle and get to your 50% that way. However, that's a lot more wire, it's a lot more receptacles, it's a lot more wall penetrations. You can also do an approach, the diagram down there, the option on the right, where you can run separate power lines to the same receptacle and you can have them powered separately. This is something that we see a lot in residential construction. This is usually, the way that it's usually done in residential is that the bottom is always on and the top is switched. The code doesn't require which one is always on and which is switched, but that's the convention that a lot of people will find familiar. And then you can switch only half the receptacle and you can easily achieve your 50% without having to do a whole lot of extra receptacles. And you just need to switch to a different type of wiring that's got an extra wire either in the conduit or in the Romex. And it's a more cost-effective way to meet this requirement. This is one of the big differences. This is not something that you can trade off by modeling. And so it's something to keep in mind as you're moving forward. Now, that switched receptacle has requirements for what the switching functionality actually looks like. So you can have automatic control devices, and you can either have a time of day controller, but if you have time of day controller, which is really just a time clock, then it has to control less than 5,000 square feet of area, can't control more than a single floor in a multi-floor building, and the occupant can't, if the occupant is able to manually override the control, can only be an override for up to 2 hours. If you don't want to do time of use controller, then you can do occupancy sensors to turn off the receptacles within 20 minutes of occupant leaving, or you can do a more sophisticated system that uses an automated signal from some other control. So if you have occupancy controls on, say, the lighting or the ventilation, or if you have, a security system, some other control mechanism that turns it off on the schedule of the building. And again, not more than 20 minutes after determining that the area is unoccupied. So you have a lot of flexibility for the control of those controlled receptacles, from very simple, when it comes down to it, the time of day controller is an inexpensive and a pretty straightforward control, to some far more sophisticated and effective control technologies. The controlled receptacles have to be visually marked to differentiate them from uncontrolled receptacles. It's just a visual mark. There's a lot of different ways that it can be done, and have to be uniformly distributed throughout the space. So you can't just, this room has switched receptacles and this one doesn't, and the 50% are over there. They have to be distributed throughout. And plug-in switching devices can't be used to comply with the requirement. So we have a lot of like occupancy or time controlled power strips that can be a very effective way to save energy, but they can't be used for code compliance, mostly because they're not permanently installed, and those power strips tend to walk away, and the energy code is really about the building itself. There are, of course, some exceptions to this. Any receptacles that are designed for equipment that's going to be on all the time anyway are going to be exempted from it, and any spaces where automatic control would cause security or safety concerns. Life safety is always going to trump energy saving requirements. Our next mandatory measure in power is for energy monitoring. And in this case, 90.1 requires measurement devices to be installed to not just monitor the electrical energy use for the building, but for energy type sub-uses separately. And those are HVAC systems, interior lighting, exterior lighting, and receptacles. And those have to be monitored separately from total. The total can either be the sum of the other monitors, or you could have a dedicated monitoring device, a dedicated meter for the total itself. Some utility meters do have an output port that allows you to connect them into a monitoring system. Some don't, so that might be an option for you. If you have a building with multiple tenants, then you have to have this monitoring separate for each tenant space. So that can be a challenging part of meeting this requirement, especially in core and shell, but the separate spaces do need to be monitored separately. There is an exception built in here. It's not an exception from the monitoring requirements, but rather it allows for a certain amount of commingling of the loads. So up to 10% of each separate load can be from other electrical loads. This might be, you've got a ventilation fan that's wired to the lighting. You don't have to wire that separately to your HVAC loads, or you just have a light in a mechanical room and everything else in that is mechanical equipment and there's just a light in there. So there's a certain amount of flexibility to make sure that you don't have to go overboard with really trying to get every little bit of those loads separated. So that's the power section, and we'll go ahead and dig into lighting now. So like I said before, we've got the prescriptive option, or you can do modeling. And this, I think, is a good way to think about how the lighting system is structured. So you have a series of mandatory requirements that apply to both interior and exterior lighting. And this covers things like controls, switching functionality, and some efficiency requirements. And then you have a set of requirements that are about interior lighting power limits, so the amount of power that can be used for lighting in the building. And you have a couple of different ways that you can comply with that building, with those requirements. And this should be familiar because this is the same structure that we had in the Oregon Code before. You can either do the whole building approach, or you can do a space-by-space approach. And then you have requirements for exterior lighting power limits. And these are also very similar to what we had in the Oregon Code before, even if the numbers are different. So let's go ahead and start with the mandatory requirement. Well, we'll do a little overview of what this section looks like. So we have the general application at the top, how the basis for compliance in 9.2. 9.4 is where we see all of the mandatory requirements. If you've been paying attention to these webinars, you might notice that ASHRAE is structured so that point 4 is always the mandatory requirements in every chapter, and point 5 is the prescriptive path in every chapter. And then we have the two options here, the building area compliance path or the alternate compliance path, which is the space-by-space method. So the control functions that we have a whole series that we'll go through here. And these are the control functionality that you have to have for your lighting. So uncontrolled lighting is really not something that's allowed under 90.1 in pretty much all circumstances. So let's start with local control. So at least one control has to control all of the lighting in the spaces for spaces smaller than 10,000 square feet. Doesn't mean that you can't have more, but at least one. And for spaces under 10,000 square feet, each control has to serve no more than 2,500 square feet. And for spaces bigger than 10,000 square feet, no control can control more than 10,000 square feet. So you see this certain amount of granularity that is required for local control so that users in the space can actually turn the lights on and off. So in most cases, all lighting has to be manual on and is not allowed to be automatic on, except for situations where manual on would endanger safety or security. A lot of times bathrooms would account for this, certain circulation spaces. And this is really the difference between vacancy controls, which are manual on, and occupancy controls, which are both auto on and auto off. There are some spaces that are restricted to partial on. So less than 50% of the general lighting power is allowed to be automatically turned on, and none of the remaining lighting automatically turned on. And we have some exceptions for this as well. Mostly open office plans, you have a certain amount of flexibility under this. We also have requirements for bi-level controls. And this means that general lighting in a space has to provide at least one intermediate step in lighting power, or between on and off, or continuous dimming between on and off. And then you have to have, We also have requirements for automatic daylighting controls. And these are triggered when you have a side lit area that has more than 150 watts of lighting, which, these days is really not a lot of lighting, or when you have a primary and secondary side lit area together with more than 300 watts. If you're familiar with the I codes, this is one of the differences that we have in ASHRAE versus the I codes. It defines both a primary and a secondary daylighting zone. If you think about how daylight penetrates a space, it gets dimmer and dimmer as you get deeper into the space. So you have part of the space that really can't be controlled by that area closer to the window that will have enough daylight a lot of the time. And so we have separate control requirements for primary and secondary, and that they have to be controlled separately for each other so that when it's bright enough in the primary zone, but not bright enough in the secondary zone, you can reduce or turn off the lighting in the primary zone while the secondary zone is at a level of lighting that is appropriate for that deeper place, a deeper position within the space. So we also have control requirements for when you have top lighting, and it's very similar when you have more than 150 watts of lighting under a top lit area. That triggers the automatic controls as well. There's also a requirement here for the automatic daylighting controls that wherever you have an overlap between top lighting and side lighting, that area should be controlled with the top lighting control. And the idea here being is that you're generally going to get longer usable daylight through your top lighting than you are from your side lighting. Then we have a series of requirements for the control systems. And these are meant to address some of the issues that have historically plagued automatic daylighting systems. Technology has gotten a lot better, and these requirements help make sure that you're getting better technology into the building. So the calibration adjustment position for the daylighting sensor is located less than 11 feet above the finished floor in a side lit area, that the calibration doesn't require the physical presence of a person at the sensor. This can be a big thing. Oftentimes you have to have, in some systems, you had to have two people to do your calibration. So this allows calibration to be done by a single person. And then there's a requirement for either continuous dimming, which is very easy with fluorescent and LED lighting, or stepped dimming that has at least one control point between 50 and 70%, and then a second control point between 20 and 40%, or the lowest dimming level that technology allows. Some lighting technologies don't, they've got a lower limit to the lighting power that is possible while still putting out light. And then a third control point that turns off all the lighting together. And so either continuous dimming, or you can think of the 3 control pointed in step dimming. And then we also have requirements to automatically reduce the general lighting power by at least 50% within 20 minutes of all occupants leaving the space, so occupancy controls. This only applies to certain space types, so make sure that you check to see that it's applying. But we do have, as always, we have some exceptions. So if the space has an LPD below 0.8 watts per square foot and it's an HID lamp, they really don't like to be turned off, which is why they are part of this. And you are reducing by more than 30%, which HID lights can do. And you have kind of an overall lighting load that's less than 0.02 watts per square foot multiplied by the gross lighting area of the building. So it's kind of a total building criteria on that. So you have a separate requirement for automatic full off for occupancy controls. And that's that all lighting automatically shuts off within 20 minutes of occupants leaving the space, and that the control device has to control an area less than 5,000 square feet. So these are the occupancy controls that will take you down to 0% lighting. And the exceptions for this are shop and lab classrooms. Any area where auto shut off could cause a safety or security concern, This is going to be especially entrances, and it'll be some corridors, any place where you might have equipment that could be dangerous if the lighting goes off. Then of course, any lighting that is intended for 24/7 operation. We also have control requirements for a scheduled shut-off, and that's that lights have to be able to be controlled on a scheduled basis. So this is automatic time switch. This can either be a time of day controller or a signal from another controller alarm. This should sound very familiar because it's very similar to the receptacle requirements. And the controller system needs to provide independent control sequences where the controls are for spaces less than 25,000 square feet. They can't be more than one floor. And this controller needs to be able to account for weekends and holidays. So this can't be a simple, same schedule every day type of controller. It has to be, it's often called an astronomical time clock controller that can account for a more sophisticated schedule. In this case too, we have requirements for the manual override. It can't override for more than 2 hours during scheduled off, and the control for the manual override has to be less than 5,000 square feet. These manual override controls largely come into play. You have the person, say, coming into an office after hours to work, but you also have cleaning staff. So there's typically not a need to have the lights come on for a longer term than that. And then of course, with the scheduled shut off, we have exceptions as well. So any lighting that's meant for 24/7 operation, patient care spaces, and then the same issues around overall lighting load and any kind of safety and security concerns. We also have control requirements for parking garage. Now, this is automatic lighting shut off where it must reduce the lighting power by a minimum of 30% when there's no activity detected. So this is an occupancy type sensor, and it's a lighting reduction. The control zone can only be 3,600 square feet or smaller. And then that's the occupancy part, but there's also a daylighting control part in parking garages that automatically reduce power by at least 50% in response to daylight within 20 feet of any perimeter wall that basically has a certain amount of wall openings. So a lot of above ground parking garages this is going to apply to. There are also no exterior obstructions within 20 feet. This is not, of course, going to apply to anything below ground or anything that has any kind of significant structural blockages to the openings in the edges of the garages. There are exceptions to the daylight requirements. So any daylight transition zones around ramps and entrances are exempt from the 30% reduction and daylight control. The idea being that you're coming from outside where the light is bright and your eyes need that opportunity to adapt to the lower light levels that are going to be in place inside the garage. We also have special control requirements for guest rooms, and this one is a big change, I think, for a lot of people in emerging technology, where similar to what we saw in HVAC, it's pretty much the same control methodology where guest room lighting and switched receptacles have to be turned off within 20 minutes of occupants leaving the space. So you would need to have control equipment in the space capable of switching these loads. There is an exception for captive key card systems. So this is a system that uses the key card to know whether or not there's someone in the space. The bathrooms need to be controlled to automatically turn off lighting within 30 minutes of occupants leaving the space. This exempts low-level night lighting. And then the supplemental task lighting, so the lamps that you always have by beds and on desks, need to be controlled by either a controller on the lamp itself or the luminaire itself, or a wall-mounted controller right there by the lamp. So none of this, you come in, you flip a switch, and it turns on all the lamps in the hotel or motel room. For those of you who are on the HVAC webinar, this is very similar, and it's this exact same control methodology that we saw, and a lot of systems are actually capable of controlling all of these things together. The code requirements were really crafted around the technology functionality that's available on the market. And then we're going to jump to the exterior. Lighting has to have dawn till dusk controls, so turning off when there isn't sufficient daylight. Any building facade and landscape lighting must be shut off between, so this is building, anything that illuminates the facade, any of the landscape lighting. And it's really meant to turn it off during off hours. The way that the requirements are phrased is that it's either midnight or business closing, whichever is later. So if your business is open after midnight, then you can keep the lighting on after that. And then it has to turn on no earlier than 6 a.m. or building own earlier. So if your business opens before 6 a.m., or a time that's established by the authority having jurisdiction, the AHJ. So you may see some set early times in some jurisdictions about when you can have that lighting come on. And then there's requirements for the power for signage lighting. Has to be reduced by at least 50% from midnight or with 1 hour of end of business operations, whichever is later, and until 6 a.m. or business opening, whichever is earlier. So that's, that should sound familiar from just a couple minutes ago. And that during any period when no activity has been detected for a time no longer than 15 minutes. So if there's no activity around the signage. So this doesn't require that the signage be turned off, but just that the light levels get reduced really when you're during that inactive time. We also have requirements for parking areas. So luminaires serving outdoor parking areas over a certain size, 78 watts, and a mounting height less than 24 feet have to be automatically controlled to reduce power by 50% when no activity is detected. And no more than 1,500 watts of lighting can be controlled together. So 78 watts is, at this point, we really are talking about parking pole lamps for parking lot lighting. Some LEDs will actually come in below that, and so wouldn't be subject to these requirements. It's all going to depend on the luminaire configuration. There are exceptions, covered vehicle entrances. Again, the idea is you want entrances to be fully lit. Exits from building and parking structures, the same condition, and any lighting integral to signage and installed by the manufacturer. So if you have any lighting that's part of a sign, you don't have to worry about retrofitting it to be controlled. And then we have power limits for the exterior lighting power. And this is based on a certain set of tables that you can see here. And this should actually look fairly familiar. It's the same basic methodology that we've had in place in Oregon before. However, some of the categories might be a little bit different and some of the numbers as we've gone to a more efficient standard. Of course, it's a combination of tradable and non-tradable spaces. These levels are generally quite easy to meet these days, and so often don't present a big challenge. And then finally, we have some requirements specifically for dwelling units, since 90.1 applies to high-rise residential, so any group R occupancy that is 4 stories or more. We have separate requirements for the dwelling units, and these really get to lighting efficacy rather than an LPD. And so at least 75% of the permanently installed lighting fixtures have to utilize lamps with an efficacy of at least 55 lumens per watt or have a total luminaire efficacy of 45 lumens per watt. This is a change from what you've probably seen before, the definition for high efficacy lamps and then a series of lumen per watt requirements. As we have moved to CFLs and LED lighting, those watt categories really don't make a lot of sense anymore. And so 90.1 has coalesced around a single rating for lamps. And then you'll see this additional one for luminaire efficacy. And this one might be a little bit confusing because the integrated LED luminaires on the commercial market are generally very efficient, but the residential style integrated LED luminaires are often not. And so this additional, this separate requirement for Luminaire efficacy in the residential side is meant to account for the fact that the integrated lamp luminaires that are available on the market for residential just don't tend to be as efficient. Outside of the dwelling units, all of those spaces need to comply with the general 90.1 lighting requirements. So now let's talk about the actual LPD portion of the code. And excuse me, this is one of the areas where 90.1 actually begins to look fairly different from other energy codes, IECC, or what Oregon had before. The basic prescriptive option does look familiar. It's just your building area method. You have a lighting power density that you are allowed for the entire building based on building type. You add up all your lighting power, you divide it by the total building area, and you make sure that it gets under that. So that part is very straightforward. We have more efficient requirements in these tables now. It should be noted though that generally you can meet these requirements without going to LEDs if you have good luminaire and lighting designs. If you have poor luminaire design or poor lighting designs, you might need to go ahead and move to LED to compensate for that fact, but we're not to the point yet where these are actually requiring LEDs. But in the space by space method that is maybe conceptually familiar, the approach in ASHRAE is very different than it is in IECC or what Oregon had before. And there's a lot to look at here, but let's go ahead and think about it a little bit more globally, and then we'll dig into that chart itself. So there are some advantages to using the space by space method. It's more flexible because you have these different space requirements. It more accurately accounts for the actual room lighting power needs. And it provides additional allowances for certain circumstances like difficult room configuration, retail needs, and any time where you might have advanced controls that the code's not requiring anymore. Really, the limitation is that you have more calculations that are needed and it's more complex. The calculation process is similar, but to the whole building method, but there's some additional steps. So first, you're looking at a space by space approach rather than the whole building. And you go to your individual spaces and you have to determine the gross lighted area of each space type. You have to include balconies, you have to include mezzanines. You use the center line for walls between spaces, and then you calculate the space power allowance by multiplying the space type area by the applicable allowance from the table, and then you sum it all together. And that's where we're going to go ahead and look at this chart. So what you see along the left there is all the different space types, and sometimes you have a high level of granularity. On office, so you have different office sizes, open plan and closed offices. Sometimes it's just a pharmacy area or different kinds of restrooms. So you start with your LPD, which is in this column here, and that part is pretty straightforward. And then you have what is called the room cavity ratio threshold, and this is one of those allowances that we were just talking about. And we'll dig into what that means in a moment. And while this makes the chart look more complex, in some ways this is actually can really help with the usability of the code. These are all the control requirements that are on the lighting in these various spaces. And so you can see that a lighting is either required, and that's the REQ. If there's a blank, that means that it's not required in that space type. And then in the control requirements for a lot of these spaces, they give you different control options. That means you have add 1 and add 2. Any place where you have add 1, you have to choose one of those control requirements, either so, and that's column B or C. And then anywhere there's add 2, then you need to choose one of those control requirements. Now this is all stated in these code sections that we just finished reviewing, but this is a real handy reference to be able to quickly see the kind of controls that are available to you. So let's talk about the room cavity ratio adjustment, one of the adjustments that you can make for the LPD. You can only use it in space by space, can't use it in whole building. And it allows you to do a calculation for a room cavity ratio. It's a ratio for room geometry that is difficult to light. And this is generally based on space height, where you have a luminaire mounting height that is very different from the work plane height. And so if your room cavity ratio based on this equation is above the threshold that we saw in the table, then you're allowed to increase your LPD allowance by 20%. For corridors and transition spaces, you can do that 20% when the space is less than 8 feet wide, regardless of the RCR. So that's in that case, they're considering that it's just going to be awkward to light. So this allows you additional lighting power to get the light from high mounted lighting down to the work plane in these awkwardly configured spaces for lighting. We also have an adjustment available for decorative lighting, which is an allowance to increase the lighting power when you're using the space by space method, but there's some conditions under which you can use it. So first, your display lighting has to be controlled separately from the general lighting and automatically controlled. And then the additional allowances can only be used for the additional lighting equipment and not for the general lighting. So that means just because you have this lighting allowance for display lighting doesn't mean that you can put in really efficient display lighting and then increase your general lighting. And the allowance varies by retail area type. So you can see here we have 4 retail areas. One is, well, anything that's not in 2, 3, or 4. 2 is for vehicles, sporting goods, and small electronics. 3 is furniture. 4 is jewelry. So each one of these is assuming a different level of additional display lighting that's going to be required for this merchandise type. And that just allows you to add additional lighting for that display lighting in that space. And then there's an option to get an additional lighting allowance based on advanced controls. So an increase in the allowance is allowed when you have additional advanced controls. Unlike the retail lighting, this allowance can be used anywhere in the building. So you can save energy through advanced controls in one part of your building and then use it for extra lighting power in another part of your building. And it's calculated as the lighting power under control. So whatever lighting is actually controlled by the lighting controls multiplied by the control factor. And the control factor comes from this table here. So you can look at these various controls on the left and the control factor allowance modification that you get in different space types. The important thing to keep in mind here is that you only get this adjustment factor when the controls are not already required in that space. So if you remember the chart that we looked at before where it had, required lighting, and then in a lot of places there were blanks, because that type of lighting control was not required in that space type. Well, anywhere that you have one of those blanks, these control factors can be used to do an adjustment in your total LPD. Now we rushed through that kind of fast because I wanted to make sure that we had some time for questions. There are a couple of places here where ASHRAE is really different. The practice is going to be really different for projects moving forward. So Connie, have we had any questions so far? And if you do have any questions, go ahead and get typing them now.
Yeah, we have not had any questions submitted at this time.
All right. We'll give people a minute or two to put some in. think while people are looking, we'll go ahead and bring this chart back up, since this is one of the big differences in ASHRAE. If people can take a look at this and see it a little bit more clearly. One thing that I would like to note about the base LPDs that are in 2016, these are already a code generation old at this point. And so the technology that's available on the market should really be able to fairly easily meet these requirements. Like I said, you can meet most of them by using fluorescence and decent luminaire design, decent lighting design. But the advent of LED lighting on the market really does give you a lot of flexibility for being able to meet these requirements, or if you're going to go through the modeled performance to begin to do some trade-offs between your building system types.
Sean, we've had some questions come in.
Great.
All right. The first question here is, this has been about ASHRAE. Can IACC be used as well?
Yes, so at the very beginning, we talked about how the state has adopted IACC 2018 as a statewide alternative method for compliance, which means that you can just use that for compliance. IACC, I would say, is more similar in structure and in requirement type to the previous Oregon code than ASHRAE is to the previous Oregon code. However, it is not quite as stringent as ASHRAE is. You can avoid the requirements around monitoring and switched receptacles in the IACC, and this methodology around the LPD adjustment factors. While it's something that adds more complexity to ASHRAE, it also adds more flexibility to ASHRAE, so it's kind of a dual-edged sword. The big thing with using 2018, of course, is that you will have the C406 optional efficiency packages that you'll need to follow in that, which is something that you don't find in ASHRAE.
Okay. Please restate the new required code for Oregon and when it will be required.
So ASHRAE 2016 is the basis, and October 2019 is when it technically goes into effect for new permit applications. We can check normally when new codes go into effect. There is a grace period for new applications being able to apply under the old code, but it was adopted in 2019, and there was a little bit of flux about when it would actually go into effect. So we'll put that in one of the answers that goes out to the group. We want to give you a specific date because that's a pretty critical question.
All right. Does 90.1 2016 require a photocell in discrete daylight zones, or can it be the same photocell and utilize offsets?
So this gets to where you have multiple daylighting zones, and in some cases you can use the same one, but I don't want to give you the wrong answer. So I'm going to go ahead and flip through my ASHRAE right now and take a quick look. But I believe that ASHRAE does not actually specify that there has to be a photocell discrete in each daylit zone. But I don't want to just sit in silence while I verify that, so we'll include that in the answer as well. I expected that lighting would have some of the more complex questions that we might need to answer.
How are designers going to demonstrate compliance? What is replacing CommCheck?
So nothing is replacing CommCheck. CommCheck is developed by by PNNL for DOE, and it is developed for ASHRAE 90.1. And that's one of the reasons that Oregon made the transition to ASHRAE, is that they can just use ComCheck without having to get a state-specific version of ComCheck created. So ComCheck will automatically always have the latest version of ASHRAE 90.1 and actually the IECC built into it. It's one of the reasons for Oregon moving to a model code away from a more homebrewed code, is it allows Oregon to more easily leverage tools like ComCheck. So ComCheck for ASHRAE 2016 is already available and it's already there for you to use. And actually for 2019, I believe is already available. So that one is available ahead of when Oregon will actually be moving to 2019.
Okay, and the last question we have on the docket right now is, what is your response to building occupants who claim the switched receptacles can be easily circumvented?
Well, the response is yes, they can be easily circumvented. But when it comes down to it, a lot of efficiency technologies that we place into buildings can be circumvented. You know, controls can be disabled, photocells can be taped over. Really, the energy code is about building buildings, requiring buildings that can be operated efficiently. Right now, the energy code does not really get much into operations, and so it doesn't require that you actually operate your building efficiently, but it does make sure that occupants are provided with a building that can be operated efficiently. And that includes having those switched receptacles available to them for some fairly significant energy savings in the types where it is required. So yeah, it's a concern, but it's one of the reasons that we're seeing switched receptacles and monitoring in the code, is to really provide occupants with that functionality that facilitates efficient building energy usage.
Okay, that was it for the question, Sean.
All right, well, thank you everyone for joining us, especially any of you who have joined us for all 3 webinars. We've got a couple of questions to follow up, so we'll make sure that that's included in the email that goes out. We appreciate you taking the time to join us, and good luck using ASHRAE in the future in the Oregon code.